Tonight, drift through one of the longest stories Earth has ever told. It begins not with dinosaurs, but with the silence they were born from. A world emptied so completely that everything which came after had to start from nothing. This is the Mesozoic era. How one lineage in the ashes of catastrophe became the most dominant force the planet has ever produced. Most stories about dinosaurs begin with the dinosaurs. This one doesn't. Before the first dinosaur left a footprint anywhere on Earth, the planet went through something that makes every other catastrophe in the fossil record look minor. 252 million years ago, the world was already ancient. Forests that had stood for tens of millions of years. Oceans packed with life from the surface to the seafloor. Ecosystems layered over each other in arrangements that had taken hundreds of millions of years to develop. Life had survived ice ages, sea level shifts, and smaller extinctions before. It had always recovered, always rebuilt, always found a way back to complexity. There was no reason from the inside of that world to expect what came next. What happened next would empty the world so completely that the rules of survival, competition, and dominance were effectively reset from zero. But the scale of what was coming had no precedent in the history of complex life. The events that had caused extinctions before, sea level shifts, regional volcanic activity, periods of glaciation, had been damaging but bounded. They had altered ecosystems without dismantling the underlying structure that made recovery possible. What began building in the Permian was different in kind, not just degree. The damage wasn't arriving from outside the planet's systems. It was being generated by those systems themselves from deep within the crust, and it was feeding back into the atmosphere in ways that touched every living thing simultaneously. But the pace made it worse. A catastrophe that arrives in a day gives nothing time to adjust, but it ends. What unfolded across the late Permian arrived slowly enough that each generation of animals and plants inherited a world fractionally worse than the one before, with no signal that the deterioration had a flaw. The chemistry of the air shifted. The chemistry of the ocean shifted. The temperatures that had held stable enough for complex ecosystems to develop across hundreds of millions of years began moving in one direction and kept moving. Nothing in the biological world had the tools to respond to a pressure that operated at geological speed while dismantling the ecological foundations that made response possible at all. But the deepest consequence wasn't the dying itself. It was what the dying left behind, not a damaged world, but a structurally broken one, where the interlocking dependencies between species had been severed so completely that the normal mechanisms of recovery had nothing to work with. The question of what came next wasn't going to be answered by what had been strongest before. It was going to be answered by whatever could function in conditions nothing alive had ever faced. The answer to what made the dinosaurs possible starts here, in a world that had nothing left to offer, anything that already existed. The Permian extinction didn't just kill species, it broke the structure of life itself. 90% of all marine species are gone, 70% of land vertebrates erased. Reefs that had stood for hundreds of millions of years collapsed and didn't rebuild for nearly 10 million more. Insect populations, the invisible scaffolding of most ecosystems, crashed. Food chains didn't weaken, they shattered from the bottom up. And the cause wasn't an asteroid or a single catastrophic day. It was slower and in some ways worse. The Siberian traps, a volcanic region covering millions of square kilometers, poured basalt floods across the land in pulses, over tens of thousands of years, pumping CO2 and sulfur dioxide into the atmosphere until global temperatures spiked and ocean chemistry fundamentally changed. The seas turned anoxic, oxygen starved, suffocating marine life from the seafloor upward. The skies dimmed. The sun still rose, but less and less could grow beneath it. What followed wasn't immediate recovery. It was silent, stretched across geological time. For hundreds of thousands of years, the planet stayed broken. Deserts spread across continents where forests had been. Scavengers moved through wastelands with almost nothing left to scavenge. The ecological roles that thousands of species had filled for millions of years, predator, prey, decomposer, pollinator, sat empty. And that emptiness is the answer. Not what died, but what it left behind. When life did begin to recover, it wasn't rebuilding the old world. It was filling a completely open one, and whatever filled it first, with the right body plan for the new conditions, would have no competition to push back against. The great dying didn't doom life. It cleared the ground for the next inheritor. The question was only, which one? If this is the kind of story you like falling asleep to, deep time, slow science, the world before we were here to watch it, alike helps more people find their way to this channel. That's all. Now, back to the Mesozoic. But the story of how dinosaurs came to exist doesn't start with the dinosaurs at all. It starts with the world they inherited, a world locked into a single landmass, baking under conditions nothing alive had faced before, filtering out every body plan that couldn't handle what the Triassic demanded. And what the Triassic demanded was very specific. The survivors of the extinction didn't wake up to a world that was simply emptier. They woke up to a world that was physically different from anything their ancestors had ever navigated. For most of the hundreds of millions of years that complex life had existed on Earth, the continents were scattered. Separate land masses meant separate climates, coastlines everywhere, shallow seas cutting between land, moisture reaching interiors, temperatures moderated by water on all sides. Life had evolved inside that geography. The bodies, behaviors, and physiologies of every animal that existed before the extinction were shaped by a world where no single place was too far from the sea. Then Pangaea locked everything together, and all of that changed. The single supercontinent stretched from pole to pole. Deep interiors sat thousands of kilometers from any ocean, cut off from the moisture that coastlines provide, exposed to temperature swings that no narrow island or coastal lowland would ever experience. What had been a planet of varied, moderate climates became something far more extreme, a world with edges that were survivable and a vast interior that wasn't. The animals that made it through the extinction hadn't been selected for this world. They had survived one catastrophe only to find themselves deposited inside a second, slower one. And the Triassic was going to be very specific about which bodies made it through. But the problem wasn't just the geography. It was what geography did to the air. With no shallow seas cutting across the interior of Pangaea, no moisture cycling inland from nearby coastlines, the atmosphere over the deep interior became something few complex animals had ever needed to cope with. Oxygen levels had dropped noticeably from what they'd been before the extinction. Not enough to suffocate anything outright, but enough to make sustained movement significantly more expensive for every animal trying to live in the new world. Walking costs more, hunting costs more. Simply maintaining body temperature in an environment with brutal daily swings costs more. But the seasonal extremes compounded the problem further. Pangaea's interior ran on a monsoonal pattern. long dry seasons with little rain, followed by violent wet seasons that arrived suddenly and then vanished. Plants adapted to those extremes pulled back to forms that could store water, resist drought, and survive fires. Low, tough, and sparse, there was no dense forest cover to moderate temperatures at ground level, no canopy to retain moisture in the soil. For an animal that needed reliable food and stable conditions to sustain growth across multiple seasons, the Triassic interior was actively hostile. But the critical pressure wasn't heat or drought alone. It was the combination of low oxygen and high locomotor demand. Any animal whose body plan required burning significant energy just to stay mobile was operating at a deficit the Triassic interior couldn't support for long. The Triassic wasn't uniformly lethal, but it was selective in ways that the Old World had never been, and most of the survivors from the Permian were carrying body plans built for a world that no longer existed. The world the survivors woke up to wasn't just empty. It was physically strange in ways that would determine which body plans could function at all. All of Earth's land masses were still fused into the single supercontinent, Pangaea, ringed by one enormous ocean called Panthalassa. No narrow seas to moderate temperatures. No mountain ranges dividing climate zones the way they do today. The interior of Pangaea was brutal, scorching heat through the day, cold at night, long dry seasons interrupted by violent monsoons along the coasts, inland deserts stretched for thousands of kilometers with almost no relief. Atmospheric oxygen sat measurably lower than it does today, which meant that breathing, just breathing and moving, cost more energy per step for every animal alive. Plants pulled back to smaller, tougher, more drought-resistant forms along highland ridges and floodplains. This is the environment that shaped the competition for what came next. Any animal that needed sprawling limbs to move, the body plan of most surviving reptiles, with legs out to the side like a lizard, burned enormous energy just walking on the flat. Any animal with a basic lung not designed to extract oxygen efficiently from thin air tired quickly, hunted poorly, and couldn't sustain the activity needed to dominate. The Triassic world wasn't neutral ground. It was a filter, and it was specifically filtering for animals that could move efficiently on 2 or 4 upright limbs and breathe in conditions that would exhaust everything else. That filter is why the archosaurs mattered. They weren't just survivors. They were built by accident of their anatomy exactly for the world Pangaea had become. And yet, surviving the Triassic and winning the Triassic were 2 different things. The world was full of animals that made it through, but only one lineage was moving in a way that cost less, covered more ground, and kept functioning where everything else was slowing down. What set them apart wasn't size, it wasn't aggression, it was something far more mechanical than either. Not every lineage that survived the Permian extinction survived the Triassic. Surviving the fire wasn't enough. What mattered was what you were built like when the smoke cleared. The early Triassic was populated by survivors, animals that had made it through by luck, by burrowing, by being small enough to hide, by eating things that didn't disappear. But surviving an extinction and thriving in what came after are 2 different problems. The world that reassembled itself in the Triassic didn't reward the same traits that had worked before. The old ecological hierarchies, which animals were predators, which were prey, which niches were taken, and which were open, had been wiped flat. Everything was up for negotiation, and the animals best positioned to win that negotiation weren't necessarily the biggest or the most aggressive. They were the ones whose bodies happened to work better in the specific, strange conditions the Triassic had produced. Among the survivors, one group was moving differently from everything else. Not faster, not larger, just differently, in a way that cost them less with every step across the hard, dry ground. Nothing in the Triassic was consciously pushing any lineage toward any particular shape, but the Triassic was punishing certain body plans and rewarding others, and across generation after generation, the distance between those that fit the new world and those that didn't kept compounding. The archosaurs were on the right side of that compounding, and they didn't yet know what it would make them. But the archosaurs were not the only survivors. The Triassic was crowded with lineages that had made it through the extinction, and many of them were not small or marginal. The Dicynodons, large, barrel-bodied plant-eaters, persisted into the early Triassic in significant numbers. Temnospondal amphibians, some reaching several meters in length, held the wetland zones. Procolophonids and various early reptile groups occupied the drier niches. The archosaurs were one thread in a world still woven from many competing lineages, and for the first portion of the Triassic, there was no obvious reason to conclude that the archosaur thread was the one that would eventually dominate everything else. But the efficiency advantage accumulated in ways that only became visible across millions of years. A lineage that burns less energy per kilometer traveled can cover more ground, occupy larger territories, sustain reproduction through lean seasons, and push into habitats where less efficient animals can't maintain a positive energy balance. None of this shows up in a single generation. It accumulates. And as the Triassic wore on, the lineages that couldn't sustain themselves in the harsher interior zones contracted toward refugia, wetter edges, cooler highlands, shrinking pockets of survivable habitat, while the archosaurs kept moving. But the split within the archosaur lineage itself introduced a pressure that the fossil record makes plain. As archosaurs diversified, they pushed into nearly every available niche: water, land, the margins between them. The lineage that would eventually produce crocodilians grew large and heavily armored, occupying the apex predator roles in many Triassic ecosystems. And that success created a ceiling for the smaller, faster, more lightly built archosaur forms still developing in the background. The same lineage, producing the ancestors of dinosaurs, was also producing their most formidable obstacle. The archosaurs didn't win because they were the biggest or the most aggressive. They won because of two mechanical advantages that compounded over every generation. The first was posture, where most surviving reptiles moved with legs sprawled out to the sides, a body plan that works but wastes significant energy fighting gravity with every step. The archosaurs carried their limbs directly beneath their bodies. The weight transferred straight down through the skeleton, the way a table stands on its legs, rather than bracing them at an angle. This made them faster, more energy efficient, and capable of sustained movement across the harsh terrain of the Triassic without exhausting themselves. The second advantage was respiratory. Archosaur lungs operated differently from the simple in and out lungs of most other animals. Air moved through in a more continuous flow, extracting more oxygen per breath, a critical edge in the low oxygen Triassic atmosphere, where inefficient breathers flagged and slowed. Pair that with stronger hearts and faster metabolisms than their competitors, and the archosaurs could move longer, hunt harder, and endure conditions that wore other animals down. These advantages didn't produce giants overnight. The early archosaurs were small, agile, cautious animals, picking their way through the remnants of a broken world, still outnumbered by the old survivors. But with each generation, the efficiency gap between them and their competitors widened, some archosaur lines moved toward the water, evolving the patient, armored forms that would eventually become crocodilians. Other lines stayed on land, growing lighter and faster. Among those, a smaller subset began to shift further, bipedal, hollow-boned, with stiffened tails for balance and grasping hands freed from locomotion entirely. Those were the first dinosaurs, and at this point, nobody would have picked them as the future rulers of anything. The archosaurs split, diversified, and produced the first animals that could honestly be called dinosaurs. But those first dinosaurs were nothing like what the name suggests today. The Triassic was already occupied by larger, better established animals that held every niche worth holding. And the earliest dinosaurs had no path through that wall except around it. There's a version of this story where the dinosaurs arrive and immediately take over, where the first dinosaur that appears in the fossil record is already something imposing. Already something that looks like the beginning of 186 million years of dominance. The actual fossil record tells a different story. The Triassic was already occupied. By the time the first true dinosaurs appeared, roughly 230 million years ago, the archosaur lineage had been diversifying for tens of millions of years, and many of those lineages were doing extremely well. Rauisuchians, large, heavy-bodied, four-legged archosaur predators, held the top predator positions across much of Pangaea. Etosaurs, armored and low-slung, grazed the vegetation. Phytosaurs hunted the rivers. These weren't struggling animals clinging to survival. They were established, successful, and numerous, occupying the ecological positions that would eventually belong to the dinosaurs. But not yet. Not for a long time yet. Into this world, the first dinosaurs arrived small, bipedal, quick, built more for agility than power. They occupied whatever spaces the larger animals had left open. They were present and they were adapting, but presence is not the same as dominance. Nothing about the Triassic was waiting for them or clearing space, and the gap between what the first dinosaurs were and what they would eventually become was so large that nothing about those early animals would have suggested what was coming. But the Rauisuchians weren't just larger, they were better established in every measurable way. Fossil assemblages from the late Triassic of South America, where the earliest dinosaurs appear, show Rauisuchians consistently outnumbering dinosaur forms in both species, count, and individual specimens. The Rauisuchians held the high-calorie prey. They held the territorial ranges. They had been in those ecosystems long enough to be embedded in the food web in ways that early dinosaurs simply weren't. Arriving into an occupied system 30 million years after the occupants had settled in is not a recipe for rapid takeover. But the dinosaurs couldn't directly challenge the Rauisuchians anyway. A 3-meter bipedal predator does not compete for the same prey as a 6-meter quadrupedal apex hunter. The early dinosaurs were filling whatever the larger animals had no reason to defend. The mid-size prey, the marginal habitats, the ecological roles too scattered to interest the dominant predators. This wasn't a weakness, it was the only available strategy. But it meant that dinosaur evolution during the late Triassic was being shaped entirely by the edges, by scraps of ecological space the larger animals had deemed not worth holding. And that is a very constrained environment in which to build anything significant. But the constraint had a consequence that cut both ways. Because early dinosaurs couldn't compete at the top, they diversified laterally into herbivory, into small prey hunting, into body plans suited for speed over power. That diversification happened across tens of millions of years in a world that wasn't paying attention to them. And the Rauisuchians, holding the apex positions with no serious challenge, had no pressure to change at all. One lineage was being shaped continuously by competition and constraint. The other wasn't. That asymmetry would only matter if the rules changed, and there was nothing in the late Triassic to suggest they were about to. The earliest dinosaurs were not impressive. That's the honest answer to what the fossil record shows. Eoraptor and Herrerasaurus among the oldest confirmed dinosaurs, dating to roughly 230 million years ago, were small, bipedal, and largely unremarkable in a Triassic world already crowded with archosaur competitors. Herrerasaurus reached maybe 3 to 4 meters in length and was a predator, but it shared its environment with Rauisuchians, large, four-legged archosaur predators that were often bigger and, by most measures, currently more successful. The Atasaurs, armored, herbivorous archosaurs, filled the plant-eating niches. Phytosaurs dominated the rivers. For tens of millions of years, dinosaurs existed as a minor element in ecosystems where other things were bigger, more numerous, and better established. The fossil record from this period doesn't show dinosaurs taking over. It shows them waiting at the margins. But waiting is not the same as standing still. Through the late Triassic, dinosaur anatomy kept refining. Lighter bones, better bipedal balance, increasingly efficient respiration. Moving faster relative to their body size gave them an edge in the spaces the larger predators left behind. Their reproductive rates may have been higher than some competitors. None of this was visible as dominance yet. It was infrastructure being built underneath a world that hadn't cracked open for them. The Rauisuchians and Phytosaurs still held the ecological high ground, and the dinosaurs stayed small enough not to threaten either. The window they needed wasn't going to come from competing harder. It was going to come from outside. For 30 million years, the dinosaurs adapted at the edges of a world that wasn't theirs. They refined, diversified, and waited. Not because they had a strategy, but because they had no other option. The animals above them in the hierarchy were too established to displace. The only thing that could change that was something that didn't come from within the ecosystem at all. For 30 million years, the dinosaurs waited. They refined their anatomy, filled marginal niches, diversified steadily into small predators and modest herbivores, and kept adapting around the edges of a world that the Rauisuchians and Phytosaurs still controlled. 30 million years is longer than the entire span of time separating us from the last common ancestor of humans and great apes. It is not a brief delay. It is an era of its own. And at the end of it, the dinosaurs were still not dominant. They were still background characters in a world that belonged to other things. What they were, though, was ready. Not intentionally, not strategically, not because any dinosaur alive in the late Triassic understood what was about to happen. But the same pressures that had kept them marginal had also been shaping them continuously, until what the dinosaur lineage had that its competitors didn't was range. Forms suited to many different ecological roles, not just the ones they currently occupied. That range was invisible as long as those roles were already taken. It would only become visible when the roles suddenly weren't. But the volcanic system that triggered the extinction didn't distinguish between competitors and inheritors. The Central Atlantic magmatic province was rupturing because Pangaea was tearing apart along geological fault lines, not because any force in nature was clearing space for the dinosaurs specifically. That atmospheric disruption removed the Rauisuchians. but it also hit the dinosaurs. Early dinosaur faunas took losses at the Triassic-Jurassic boundary. The extinction was not a targeted removal of competitors. It was a generalized catastrophe, and the dinosaurs survived it rather than escaping it. But the losses weren't equal. The Rauisuchians, phytosaurs, and etosaurs were gone completely, not reduced, not pushed into refugia, but extinct across their entire range. The dinosaurs lost species too, but the lineage survived, and more importantly, the varied body plans that had accumulated across 30 million years of marginal diversification survived with it. The extinction erased the dominant forms and left the generalists. That asymmetry, complete loss for the specialists at the top, partial loss for the varied lineage that had never held the top, determined everything that came after. But the world the dinosaurs expanded into was not immediately hospitable. The Triassic-Jurassic boundary is marked in the rock record by a significant disruption in plant life. A fern spike, the same post-catastrophe vegetation pattern that appears after every major extinction, indicating that complex plant ecosystems had collapsed before recovering. The early Jurassic was not the productive world the sauropod giants would eventually inhabit. It was a recovering world, still unstable, with food webs reassembling from whatever had survived. The niches were there to be filled, but whether the dinosaurs could expand fast enough before something else did was not guaranteed. Roughly 201 million years ago, the world broke open again, and this time the dinosaurs were on the right side of it. The Central Atlantic Magmatic Province, a massive volcanic system activated as Pangaea began to rift apart, sent another pulse of carbon dioxide and sulfur into the atmosphere. Global temperatures spiked again. Acid rain fell across ecosystems already under stress from the shifting climate of a fracturing continent. The Rauisuchians, the large archosaur predators that had kept dinosaurs at the ecological margins for tens of millions of years, were gone within a geologically short window. The phytosaurs vanished. The etosaurs disappeared. The competitors that had held every major niche against the dinosaurs were removed, not by the dinosaurs themselves, but by a planet that kept resetting its own board. The ecological vacuum that opened was enormous, and this time the dinosaurs were positioned to fill it. They had already spent millions of years diversifying quietly, small predators, mid-size herbivores. Varied body plans, so when the niches cleared, there was already a dinosaur form suited to step into nearly each one. They didn't need to invent new body plans from scratch. They expanded into space that had just opened, and they did it fast. Within a few million years of the Triassic-Jurassic boundary, dinosaurs were the dominant large animals on land across most of the planet. This was the actual conquest, not a war they won, but a vacancy they filled, backed by 30 million years of quiet preparation. The extinction removed the competitors. The dinosaurs expanded, but expansion and size are not the same thing. And in the early Jurassic, the dinosaurs that spread across the land were still modest, still mid-range, still nothing that would stop you in your tracks. The reason they became giants hadn't arrived yet. It was coming from the ground up, and when it came at a scale the planet hadn't produced since the Permian. After the Triassic-Jurassic extinction cleared the competitors, dinosaurs spread across the land. But spread is not the same as grow. The early Jurassic dinosaurs were still, by later standards, modest animals, predators in the medium range, herbivores that browsed low vegetation. Nothing yet that would stop anyone in their tracks. The world had opened for them, but the world hadn't yet given them a reason to become enormous. That reason was coming from the ground. As Pangaea fractured and the continents began their slow drift apart, the geography of the planet started changing in a direction that would transform what was possible for any plant-eating animal. New coastlines formed where there had been interior desert. Rainfall patterns shifted inland. Temperatures stayed warm but stabilized, losing the violent extremes that had defined the Triassic. And in that warmth and moisture, plant life responded in a way it hadn't been able to for tens of millions of years. Conifers spread across entire continents. Ferns and cycads carpeted the understory. The planet's vegetation, after tens of millions of years of drought-adapted stunted forms, began producing biomass at a scale it hadn't managed since before the world broke. The food supply didn't just increase, it became vast, stable, and layered from the ground to heights nothing had reached in tens of millions of years. But plant abundance alone doesn't produce giant animals. It produces the possibility of giant animals, which is a different thing. The early Jurassic herbivores that inherited the vacant niches were still modest in size. Small sauropod precursors and ornithischians browsing low vegetation. Nothing yet that suggested the multi-ton behemoths that would follow. The food was becoming available, but turning available food into extreme body mass requires a skeleton that can bear that mass, a digestive system that can process vegetation fast enough to fuel it, and a cardiovascular system that can move blood through a body measured in tens of meters. None of those adaptations appear overnight. But the sauropod body plan turned out to contain a solution to the weight problem that no other large land animal in Earth's history has independently developed. The bones weren't solid. They were structured in a way that shed mass without compromising the structural demands of supporting a body that size. Something no other large land animal lineage independently arrived at. This is why sauropod size kept increasing across the Jurassic rather than plateauing. The usual constraint that brings gigantism to a halt in other lineages was being bypassed by something built into the sauropod skeleton from the beginning. But size on that scale created its own pressures. An animal that needed to consume vegetation continuously just to sustain its body couldn't stay in one place. It had to move constantly across the landscape. And in moving, it remade that landscape whether it intended to or not. Sauropod herds opened forest gaps, suppressed certain plant species, and compacted soils along routes they traveled repeatedly. The vegetation system that had produced the giants was now being altered by the giants themselves, and those alterations had consequences for every other species sharing that landscape, including the ones that had started hunting them. The Jurassic world that opened after the extinction was nothing like the Triassic one that came before, and that difference is why the giants were possible. Pangaea was breaking apart, and the rifting created new coastlines, new shallow seas, new weather patterns reaching into what had been arid interior zones. Rainfall increased. Temperatures were warm but more stable. Conifer forests, some reaching over 30 meters in height, spread across entire continents. Ferns and cycads carpeted the undergrowth in dense layered canopies. The productivity of plant life surged to levels the Triassic never reached, and it stayed there, reliably, season after season, across millions of years. For a herbivore, this was as close to unlimited food as the planet has ever produced. The sauropods, the long-necked quadrupedal plant eaters, took that abundance and turned it into body mass. Brachiosaurus reached 18 meters in height, accessing canopy vegetation nothing else could touch. Diplodocus stretched 27 meters in length, sweeping its neck across vast feeding arcs at lower levels. Their bones were not solid. Air sacs threaded through the skeleton itself, making their enormous frames lighter than they appeared. The largest individuals may have consumed close to 400 kilograms of vegetation per day, which required constant movement and shaped the landscape around them. They were not just living in their environment, they were restructuring it, opening forest gaps, controlling which plant species dominated, determining where smaller animals could and couldn't live. The abundance of the Jurassic produced the giants, and the giants produced the world that everything else in the Jurassic was navigating. The sauropods kept growing, generation after generation, pushing the upper limits of what a land animal could physically be. The food was there. The body plan worked. Nothing in the Jurassic was pushing back against the growth until something caught up. An ecosystem with animals that large, moving in herds across open landscape, wasn't going to stay without hunters capable of taking them. And the hunters that emerged weren't operating the way anyone expected. The Jurassic was, for the sauropods, a period of almost uninterrupted expansion. The food was there. The climate held. The body plan worked, generation after generation. The upper limits of sauropod size crept higher as larger individuals accessed vegetation that smaller ones couldn't reach and produced offspring that inherited the same tendency toward scale. Diplodocus, Brachiosaurus, Apatosaurus, animals whose existence still seems improbable when you look at a reconstruction, were not aberrations. They were the predictable output of a system where food was abundant, the body plan was proven, and the environment offered no resistance to growth. Nothing, that is, until the predators caught up. An ecosystem with animals that large, that numerous, and that slow-moving was not going to stay without hunters capable of taking advantage of it. The theropods, bipedal, fast, and already well established as the dinosaur predator lineage, had been tracking the herbivore escalation the whole time. And by the late Jurassic, they had produced something that matched the scale of what they were hunting. Allosaurus was not the largest theropod that would ever exist, but it was the first for which the fossil evidence starts telling a more complicated story than a single animal hunting alone. But hunting a sauropod is not a problem that individual ambushes solve. The prey is too large, too heavy, and, despite appearances, not as slow as the size suggests. An adult Diplodocus could sweep its tail at speeds fast enough to injure a large predator. Brachiosaurus could rear on its hind legs. The sheer mass of a healthy adult sauropod made a solo attack from any predator in the Jurassic not just difficult, but potentially fatal for the attacker. Any theropod that made a habit of solo attacks on large, healthy adults would select itself out of the population faster than one that found a better approach. But the fossil record suggests theropods found that better approach, and what it preserved is specific enough to resist simple explanations. The pattern across multiple sites isn't consistent with solitary hunting or opportunistic scavenging. It points towards something more organized, more deliberate, and more socially demanding than the standard image of a lone predator acting on instinct. The evidence didn't emerge from a single excavation. It accumulated across decades of fieldwork in separate locations, and each site reinforced what the others had suggested. But if theropods were operating with that level of coordination, the behavioral implications run deeper than hunting strategy alone. The cognitive load of tracking multiple individuals, adjusting to their movements, and responding to shifting conditions mid-hunt is not trivial. It is the kind of demand that, in any lineage, tends to select for more complex neurology over time. And by the late Jurassic, the theropod lineage had been under exactly that demand for millions of years. Giants on that scale created an arms race, and the theropods ran it. Allosaurus, the dominant large predator of the late Jurassic, reached 11 to 12 meters in length and hunted prey that often dwarfed it. Fossil evidence points to more than solitary ambush. Bone beds where multiple Allosaurus individuals died in the same location, trackways showing parallel movement patterns, and bite marks on sauropod bones suggesting repeated feeding by multiple animals. The picture that emerges is coordinated hunting, something organized enough to bring down prey far too large for a single animal to overpower, which required a level of social intelligence that significantly complicates the old image of dinosaurs as solitary, instinct-driven creatures. Velociraptor and other dromaeosaurids showed similar evidence: fossil groupings, shared den sites, anatomy suited for strategic positioning rather than raw speed alone. The escalation this produced across millions of years drove predator body plans toward faster reflexes, sharper binocular vision, and increasingly complex behavior. It drove prey toward herd movement, larger size as a defense, and, in some lineages, active weaponry: the armored tail clubs of ankylosaurs, the spiked shoulders of certain sauropods. Every adaptation in the predators produced a counter-adaptation in the prey, and every counter-adaptation in the prey pushed the predators further. By the end of the Jurassic, the dinosaur world was not a collection of large animals living independently in the same space. It was an interlocked system of ecological pressures, each species shaping the constraints that every other species had to navigate. The predator-prey arms race that defined the Jurassic didn't stop when the Jurassic ended. It carried forward into a world that was physically changing beneath the dinosaurs. Continents pulling apart, populations separating, each isolated landmass running its own version of the same evolutionary experiment. What that separation produced over tens of millions of years was something the connected Jurassic world never had time to build. The Jurassic ended, but the dinosaurs didn't. What changed was the world beneath them. Pangaea's breakup, which had been gradual through the Jurassic, accelerated into the Cretaceous, and the continents that pulled apart carried their dinosaur populations with them into increasingly separate evolutionary trajectories. What had been one connected dinosaur world started becoming many. South America developing its own predators and giants, Asia generating lineages that never reached the Western continents, the landmass that would become North America running its own long evolutionary experiment in isolation. The planet was, in a sense, running parallel versions of the dinosaur story simultaneously, each on a different continental stage, each with different vegetation, different climate pressures, and different competitors shaping the outcome. Within each of those separate worlds, the refinement that had been building since the Triassic kept accumulating. Predators grew larger, more specialized, more neurologically complex. Herbivores developed weaponry, horns, armor, herding behavior that pushed predators to develop better strategy in return. The Cretaceous was not just more of the Jurassic. It was the Jurassic's logic taken further, for longer, across more diverse environments, producing animals at the end of the period that were measurably more capable than anything the Jurassic had generated. At the top of that accumulation, in the late Cretaceous of North America, sat one animal, and it was Tyrannosaurus rex. But the separation created a problem alongside the opportunity. As dinosaur populations drifted apart on separating landmasses, the gene flow that had connected them was severed, Species that had been part of the same population became isolated, and isolation drives divergence. The same pressures, operating on genetically separate populations, produced different outcomes over millions of years. What had been a relatively coherent dinosaur fauna across Pangaea fractured into distinct regional lineages, each developing in directions the others weren't tracking. But divergence under isolation also produced escalation that had no equivalent on the connected landscape. Herbivores on each landmass evolved under the predator pressure specific to that landmass. Predators refined against the prey available to them locally. The refinement happening on each separate landmass was calibrated to local conditions, which meant the Cretaceous was producing more specialized, more capable animals than the Jurassic had, not because evolution accelerated, but because it was running more parallel experiments simultaneously, with nothing averaging the results back toward a common form. But each of those separate experiments was converging on a local apex, and that position on any landmass had room for only one occupant at a time. In Western North America, the lineage converging on that position through the late Cretaceous had been building toward it for tens of millions of years, each successive form more heavily built, more sensorially capable, more precisely matched to the prey community around it. What eventually emerged wasn't an improvement on the Jurassic predators. It was something those animals couldn't have become, given how much less time they'd had. If the Jurassic built the structure of dinosaur dominance, the Cretaceous refined it into something that covered the entire planet. By the Cretaceous, the breakup of Pangaea had produced separate continents, each developing its own distinct dinosaur fauna in isolation. South America had its own giants, Asia had its own predators, Africa, Australia, and the land masses that would become Europe each generated lineages that diverged from their common ancestors under different climates, different vegetation, and different competitive pressures. The result was not one dinosaur world, but many, all running simultaneously on the same evolutionary engine. This continental diversification is why the Cretaceous fossil record is so dense. Dozens of distinct ecosystems, each producing its own set of apex species. Tyrannosaurus rex, emerging in the late Cretaceous of North America approximately 68 million years ago, was a product of this long refinement. Its bite force was roughly 6 times greater than a great white shark's, enough to crush bone and extract marrow in a single clamp. Its olfactory bulbs were proportionally enormous, giving it a sense of smell comparable to a modern vulture. Its binocular vision, unusual for a predator of that size, suggests active hunting rather than pure scavenging. For roughly 2 million years, until the asteroid impact at 66 million years ago, Tyrannosaurus held the apex position in one of the most productive terrestrial ecosystems the planet had produced. That was the full height of the conquest, 186 million years after the first small dinosaurs appeared in the Triassic margins, waiting for their moment. By the late Cretaceous, dinosaurs had reached the apex of what land could produce, but the conquest the title describes was never only about land. While the dinosaurs were refining on the ground, the same lineage that produced them had already been moving into the air and the ocean, and what filled those spaces during the peak of the Mesozoic was not what most people picture when they think about what lived alongside the dinosaurs. Through all of this, the extinction, the Triassic recovery, the Jurassic expansion, the Cretaceous refinement, the story has stayed on land. The land is where the dinosaurs lived, and land is where the drama is easiest to follow. But land was only one of the planet's 3 inhabitable realms, and the Archosaur lineage that produced the dinosaurs was not content to leave the other 2 to whoever else might try to fill them. The skies above the Mesozoic were not empty. They were not, for most of the era, populated by birds. Birds came later, slowly, from within the dinosaur lineage itself. What filled the air from early in the Triassic onward was something else. The pterosaurs, archosaur relatives that developed flight independently from any ancestor they shared with the dinosaurs. And that evolved across the entire length of the Mesozoic into forms that grew progressively stranger and larger. Meanwhile, in the oceans, an entirely separate set of reptile lineages had taken to the water, and the seas of the Mesozoic were anything but quiet. What lived in those oceans during the peak of the Mesozoic was not a collection of oversized fish, but the air presented engineering problems that the land didn't. Flight requires a power-to-weight ratio that strict scaling makes increasingly difficult to maintain as body size increases. The larger a flying animal gets, the more muscle mass it needs to generate lift. But more muscle mass means more weight, which requires even more lift. At a certain size, the math stops working for most body plans. Birds today rarely exceed 15 kilograms. Bats are smaller still. The pterosaurs, however, kept growing across the Mesozoic in defiance of what seems like a hard physical ceiling, and the question of how they managed it has no simple answer. But the oceans presented a different kind of challenge. Occupying them required not just getting into the water, but evolving the full suite of adaptations that sustained aquatic predation. Streamlined bodies, limbs converted to paddles or fins, lungs capable of handling extended breath holds, sensory systems recalibrated for an underwater environment. Each of those changes took millions of years, and each marine reptile lineage that entered the ocean during the Mesozoic had to solve those problems independently. The ichthyosaurs solved them so completely that their body plan converged on the dolphin, an animal that wouldn't evolve for another 150 million years, because the physics of fast aquatic hunting produced the same optimal shape regardless of the lineage doing the hunting. But the ocean didn't stabilize once it was occupied. New lineages kept entering, and each arrival disrupted the hierarchy that the previous occupants had established. The predator structure of the Mesozoic ocean wasn't a system that filled once and held. It was a competitive environment that kept reshuffling from within, with established dominance offering no guarantee of permanence against a lineage that arrived later with a different set of capabilities. The land was never the whole story. By the middle of the Mesozoic, the archosaur lineage and its relatives had moved into every available space on the planet. Pterosaurs, not dinosaurs, but close archosaur relatives, took the air. Early forms were small, but by the Cretaceous, Quetzalcoatlus reached an estimated wingspan of 10 to 11 meters, roughly the span of a Cessna's wings, and almost certainly walked upright on land before launching into flight from a standing position. The oceans, meanwhile, were occupied by a succession of marine reptile lineages. Ichthyosaurs appeared first, dolphin-shaped animals with large eyes suited for deep water hunting, some estimated to have reached 20 meters in length. Plesiosaurs followed, long-necked, paddle-driven, persistent hunters of the open ocean. Mosasaurs arrived later in the Cretaceous and became the dominant ocean predators, displacing the ichthyosaurs and growing to 17 meters or more. None of these were dinosaurs in the strict taxonomic sense, but they were all part of the same radiation. The archosaur expansion that began in the Triassic with two mechanical advantages and spread over 180 million years into the air above every continent and the water of every ocean. When paleontologists describe the Mesozoic as the age of reptiles, This is the scope they mean. Not one group of animals dominating one environment, but an entire lineage filling every layer of the biosphere simultaneously for longer than mammals have yet existed. The Archosaur lineage had filled the land, the air, and the ocean simultaneously for over 150 million years. Then the asteroid hit, and most of it was gone within a geologically brief window. But not all of it. Something survived, and what survived carried more of that 180 million year history than the extinction had any reason to leave intact. The question is what that looks like today. The asteroid that struck the Yucatan Peninsula 66 million years ago is where most tellings of the dinosaur story end. The impact, the darkness, the cold, the collapse of food chains, it is a clean ending, a hard stop, the moment the Mesozoic closes and something else begins. And in terms of the non-avian dinosaurs, the giant forms, the tyrannosaurs and sauropods and horned ceratopsians, that ending is real. They were gone. The world that came after belonged to the mammals that had been living in their shadow, and the dinosaur chapter seemed closed. But the fossil record had been steadily accumulating evidence for decades that the ending wasn't quite that clean, that something from inside the dinosaur lineage had been changing long before the asteroid arrived, producing forms that were becoming something else with each passing million years, until the line between dinosaur and bird had blurred past the point where any honest paleontologist could draw it sharply. By the time the asteroid hit, one branch of the theropod family tree had already become something that could survive what was coming. The question of what survived and what it left behind has an answer that most people haven't fully considered. But the asteroid didn't end everything equally. The same impact that removed Tyrannosaurus and Triceratops and the last of the giant sauropods also removed the pterosaurs, the mosasaurs, and the plesiosaurs, essentially clearing the large body ecological space across land, air, and ocean simultaneously. The scale of the removal was so complete that the world after the impact had more open ecological space than it had seen since the Triassic-Jurassic boundary. And the survivors, small, opportunistic, able to eat whatever remained, were suddenly in a world with no competition at the top. But among the terrestrial survivors were the small feathered theropods that had been diversifying through the Cretaceous in the shadow of the larger dinosaurs, occupying the niches the giants had no interest in. The insect eaters, the seed dispersers, the animals small enough to hide in burrows and survive on whatever the post-impact world still offered. They had gone unnoticed precisely because they were useful only in the margins, and the traits that had kept them there, small size, varied diet, flight capability in the most derived forms, were exactly the traits that let them survive an event that removed everything above them. But the connection between those survivors and the living world runs deeper than survival alone. What made it across the boundary wasn't just a lineage that happened to be small enough. It was a lineage that carried intact the anatomical foundations of everything that lineage had built across 180 million years. The extinction removed the giants. It didn't erase what the giants had been made of. The asteroid that struck the Yucatan Peninsula 66 million years ago ended the Cretaceous in fire, darkness, and cold. Non-avian dinosaurs were gone within a geologically brief window after impact. But the lineage didn't end. Birds are classified within Theropoda, the same group that produced Velociraptor and Tyrannosaurus. Feathered dinosaurs existed well before the asteroid. Anchiornis, Microraptor, Archaeopteryx, animals with flight feathers and wishbones already in place tens of millions of years before the impact. The transition from feathered theropod to bird was already well underway through the Cretaceous, not something that scrambled together in the aftermath. The air sac system threading through sauropod skeletons is the same system inside a bird skeleton today. The hollow shafts, the fused clavicles forming the wishbone, the hip arrangement, all continuous from non-avian dinosaurs through every living bird species. Roughly 10,000 bird species are alive right now, on every continent, in every climate zone the planet has. The footprints left in Jurassic and Cretaceous rock still exist in exposed formations on multiple continents. Trackways recording the stride length, the weight distribution, and the direction of travel of animals that walked those surfaces 150 million years ago. The bones of sauropods pulled from Morrison Formation rock in the American West still carry the traces of the air sacs that made those bodies function. The conquest that began in the ashes of the Permian accelerated through 2 extinction windows, peaked across 186 million years of continuous dominance, and never really ended. It just changed shape. The line from the first small Triassic dinosaur waiting at the margins to the bird outside your window is unbroken. If you made it this far, you already know whether this is the kind of place you want to return to. The subscribe button is there if it is. Sleep well.